Hi everyone, thank you all for joining. My name is Navdeep Sharma. I'm a data and AI architect at Accenture The Dock. First of all, I would like to thank Shift AI for moving forward with this conference to prove how important and also how effective remote communication can be. Today, I'm going to present one of our work in the doc, which is Algorithmic Fairness. The agenda for today, it's not very long. I hope to cover all of it. Uh, First, we'll go over algorithmic bias and what is the importance of treating algorithmic bias in today's age. Second, we'll go over some of the definition and key terminologies that we need to know before treating the algorithmic bias. Third, we'll look into some of the fairness metrics that we particularly use as part of our research and development. And then last, we'll go over to the demo of Accenture Fairness Tool, which is designed to treat the biases in the data as well as machine learning model. Okay, what is algorithmic fairness? So the very definition of algorithmic fairness should be derived from the business as well as business's impact on individual people. But on a very generic term, algorithmic fairness is a practice that aims to mitigate unconscious bias against any individual or any group of people in machine learning. As we rely more and more on machine learning and data driven automated decision making, it's important that for any new solution, businesses needs to consider society as a key stakeholder in their process. In designing the solution, or basically looking into some of the a fundamental thought process of different data scientists, there are two very contrasting thought process. First, the model summarizes the data correctly. If the data is biased, it's not the algorithm's fault. The data biases are inevitable. We must design algorithms that account for them. So we certainly believe in the second opinion and second thought process, where whenever we are looking into designing any machine learning model using historical data, we take this assumption that historical data does not accurately represent the current society. Moving forward to show some of the examples which occurred in past few years. One of the most popular one was when Google Photos tagged a black woman as gorilla. Google reportedly fixed it, but the way they fixed it, they had to rule out some of the gorilla or chimpanzee tags out of their image labeling technologies. So it gives an example of how deeply the biases are embedded in the data sets. Another very example about the biases is Amazon had to scrape an internal AI recruiting tool because the tool was biased against women, which proves the point that you can't really take historical data, or for many of the cases even current data, to train your machine learning, because most of the big tech firms have higher ratio of men for technical jobs as compared to women. So now let's get familiar with the terminologies used in the algorithmic fairness field, and we're kicking off with the definition of the group fairness. Group fairness has a key terminology, protected feature, and protected feature is the attribute of personal data which can directly contribute to discrimination, such as race, gender, and nationality. EU laws prohibit discrimination on ground of nationality, gender, and other protected attributes as well. However, since the guidelines are useful in the identification of their protected feature, there is also responsibility to define privileged and unprivileged status to the categories of people that fall under this categorization. Such as in this particular example, for race, we can define whites as a privileged and black as an unprivileged group. Whereas the unprivileged group can be regarded as a group of people who qualify for social protection by law or policies. So if we take an example of criminal risk assessment use case, where race has proven to be a common factor for discrimination, based on this attribute, one partitioning the population into white defendants and black defendant can we can designate white dependent as a privileged population and black dependent as an unprivileged population. Group fairness approaches the partition of the sample into groups and seeks to equalize a statistical measure across the group. Moving on, the individual bias is actually a harder problem to treat, whereas the very definition of individual bias is individual bias seeks to understand if similar individuals are treated similarly irrespective of their membership to any of their groups. Here are some of the key metrics that we used as part of our research and development phase. We'll go through each one of them in detail, but the ones in orange are the one that we implemented, but on the right hand side the gray ones are the one which we didn't implement, and the decision was basically taken based on the use cases and popularity as well. So to actually put in perspective that when to use which fairness metrics, it's important to understand that it depends on the use cases. Some of the fairness metrics which may be suitable for HR screening might not be suitable for criminal justification. Okay, let's go to the mutual information. So mutual information is the first fairness matrix, and in our case mutual information is an exploratory tool for capturing relationship between protected and non-protected factors. It quantifies how much information is communicated on average in one variable, say education, about another variable, let's say race. So even if race is not explicitly used in training the model, education can be used as a proxy in the model and influence the bias in the model as well. The visualization on the right hand side is from the Accenture's Fairness Tool, but the whole idea of mutual information is find the relationship between protected and non-protected attribute. To give another example, if in the historical data men used to work higher number of hours during per week, and women had lower number of hours, and if your loan application uses that as a criteria, even if they don't have a gender as a parameter, the loan application can still be influenced by the number of hours property. So that's mutual information. Let's move forward to prevalence. So prevalence for a given outcome is the fraction of population that satisfies that outcome. So in the use case where we are considering prevalence for reoffense, it is defined as the fraction of population that has reoffended in criminal records. In a fair machine learning algorithms, we typically calculate prevalence for each of the subgroups of the protected feature, and we then compare two subgroups which is divided into privileged and non-privileged classes, and try to build a ratio between privileged classes and non-privileged classes. If the ratio is equal, and if the ratio is equal to 1, then it's completely balanced data set, but a lower ratio will determine higher imbalance in the data. So prevalence is actually the next step in our workflow following the mutual information, as it gives really good understanding if there is any bias exist in the data set or not. So let's move on to the next algorithmic fairness matrix, which is disparate impact. A disparate impact occurs when a selection process has a widely different outcome for different subgroups in the data set. In our example, disparate impact, we're comparing the proportion of black population classified as risk to reoffend as compared to population of white. When we compare these two by fraction, we're calculating the disparate impact ratio, which is very similar to the way we calculated the prevalence. We first calculate the false positive plus true positive divided by total data set. Then we calculate for the privileged group as well, which is same, false positive plus true positive divided by total sample size. The disparate impact ratio, which is 30% in this particular case, is very close to the prevalence, which actually just telling the story that the biases are embedded in the data set. Disparate impact usually has a threshold value of 0.8. So any disparate impact ratio less than 0.8 defines as a higher imbalance in the data set. And it's also known as 4/5 rule. Okay, let's move on to the next algorithmic fairness matrix, which is false positive rate. Calculating parity for false positive rate implies that the false positive rate are equal among the privileged and unprivileged populations. So in this particular example that we have been using, false positive equates that conviction of an innocent. And let's say that we have divided our population into two parts, black and white. Black is unprivileged and white is privileged. If we look at the confusion matrix on the top right, the false positive rate for black population is 0.063, whereas false positive rate for white population is 0.013. In this hypothetical scenario, the false positive rate of unprivileged group is close to 4 times higher as compared to privileged group. We also have the error ratio for a given protected variable. The way error ratio is defined is as a ratio of error in the privileged population to the ratio of error in unprivileged population. Going bit into some of our learnings while we went through different phases of this project. Algorithmic fairness requires input from different social elements such as law, non-discrimination law, and also it also requires us to continuously monitoring the impact of our machine learning model on individuals' life. It's very aptly written. Bias is feature of a statistical model, whereas fairness is feature of human value judgment. And while we treat the biases in the historical data and we shift towards future and we use more new data, we really hope that there will be much less bias and we will hopefully be moving towards an equality of the system. Looking at some of the technical challenges we faced, metric selection was definitely one of the challenges, and it's always recommended to give higher thoughts on which metrics to consider while looking into treating the biases. And all the metrics are not equal. Obviously, the results are different, but obviously, computationally, they are differently expensive as well. So, for an example, disparate impact is much more computationally expensive as compared to mutual information or predictive parity. Second challenge was academic and industry gap. Academic research has been soaring in past few years around algorithmic fairness, but in the industry, there is no really a tool tools or utility which can treat the algorithmic bias at large scale of the data. Non-binary protected feature such as nationality, we've been taking example of nationality and privileged and unprivileged classes as whites and blacks respectively, but obviously it's a non-binary feature. You can have more than just black and white. You can have Asian and others. Looking into other issues, more than one protected feature, handling that has been one of the constraint as well. Treating the biases in the data by looking into gender, race, and other protected features, let's say salary or address or area of residence. Final challenges that we faced was looking into legislation, keeping ourselves up to date, and the general guidelines and recommendation around how to treat biases in the data set. So let's look into the tool itself. So Accenture Fairness Tool actually combines the perspective of data scientist and business stakeholder. Data scientist starts with the tool. They use the Accenture Fairness Python library to import into the Jupyter Hub, which is connected to to a web portal where the data scientist can publish the reports and analyzation of the fairness of the data. And then business users can look at the reports on the web portal, and they can actually make very informed decisions about which variable or which features needs to be treated with bias measurements. Going back, this is particular notebook which is looking into customer analytics data, where we're trying to predict customers with higher salary ranges. So we've broken into the greater than 50,000 versus less than or equals to 50,000, and that's our favorable class is greater than 50,000. In this particular library, the way we import the library is we import the Accenture Fairness, and we create a dataset class, and we connect to the web portal, which could be any addresses, and then we download the data. Here are the features which is existent in the dataset at the moment, and the way we are trying to treat the biases, our protected attribute is sex, and male is our privileged classes. So let's look into the mutual information metrics that we've gone over. It's similar results to what we've already gone over in the PowerPoint presentation. Obviously, marital status is highly related to relationship, but there are other relationship like sex is related to relationship as well. Then looking into the disparate impact, we can clearly see that the male is more dominant as in greater than 50,000 category as compared to female. So to treat this bias, if we're trying to predict to treat this bias, we at least know now that the number of female samples at the moment is a lot lesser in greater than 50,000. And also, since we talked about 80% of disparate impact, the ratio is 0.3, which is close to 30% disparate impact ratio, which is a lot lower. And by going through each data point, which is the repair level, you can see the changes that needed to be done in each of the data set to fix that bias. So this is basically the reports that is being generated using the visualization of the tool. Then you can publish these reports, call it any name, adult dataset, and you publish the reports. This successfully gets published, and then you come out to this portal where you should most probably be able to the Shift AI reports, which is just published, and the business user can log in and look into the reports and look into different aspects of your data and treat fairness and take more informed decision for that matter mainly. Thank you so much for being with me. That's pretty much it for my side. I hope there would be something useful coming out of these sessions. You can reach out to me for any questions on navdeep.a.sharma@accenture.com. That's pretty much it. I hope you enjoy the rest of the sessions. Thank you.